right, first question. You will guaranteed see a graph like this on the test. And there's a couple different things I could ask about it, so I just asked a whole bunch of stuff about it as samples. So the first thing it asks you to do is to label the EA, which stands for what? Activation energy. So what is the activation energy with the enzyme? With the enzyme would be B. So with would be B. Keep in mind, to get the activation energy, it's from the starting point. Imagine you're trying to push a rock to the point where it would roll down the hill on its own. So this is my starting point. This is the energy in my reactants. I would have to push them with an enzyme because enzymes lower it from this starting point to the top of the hill, which would be this. So that's B. What about without the enzyme? So without the enzyme would be C. I'd have to push them from the starting point to the top of the hill, the higher hill. The way enzymes work is they lower activation energy. That's what they do. That is exactly what they would want you to recognize in a graph, is that the little hump would be lower. Next, delta G. Which letter is that? D. So delta G is just the net energy change. So in other words, if you turned this into a bar graph and we just look at the reactants, this is how much free energy they have, and the products, this is how much free energy they have. There's less energy in the products than the reactants, which means that delta G, which is D, is it spontaneous or not? Yes. So this yes is spontaneous because delta G would be a negative number. If there were actually numbers here, you'd subtract. So this could be like 10, 20, 30, 40. So the products would have 10, the reactants would have 40, and so delta G would be negative 30 joules or whatever the units are. So if delta G is a negative number, it's spontaneous. Or what's the other word for a reaction that gives off energy? Exergonic. So this would be an exergonic reaction. The opposite, if you were to see this, would be endergonic or non-spontaneous because the products now have more energy than the reactants. So energy would have to have been put in, maybe by ATP or whatever, but this would require energy. Olivia, question? No, it would be like this. I mean, I could give you a bar graph too, but a bar graph's easier. What you can't see in the bar graph is activation energy. You can see clearly the net change, but the purpose of this graph is to show activation energy. All right, then the last part, reverse. I was not specific here. If I was going to ask this on a test, I would have to say with the enzyme or without the enzyme because they're actually two different numbers. So activation energy, if I was going to go backwards, let's just say without the enzyme. What would be the letter for that? That would be E, because I would have to start here, imagine I'm going the other way, and push it all the way to the top of this hill. So E would be without the enzyme. And what if I had the enzyme? What would it be then? Right, so EA with the enzyme going the other direction would be A, from here to the top of the lower hill. Honestly, that's every possible question I could ask on this picture. So if you understood those, you should definitely get any questions about this graph right. Yay, I know, right? All right, this graph. So what this graph is showing, imagine, remember, in the lab, we were one enzyme. You were one person ripping papers. That's not how enzymes really work. So in reality, you might have 100 enzymes. So you have a beaker or a box or whatever, and there's 100 enzymes in here. If I start adding substrate for this to break down, and I add 10 molecules of substrate, 10 of those enzymes are going to be activated. Let's say I add 20 instead. 20 of the enzymes are going to be activated. I add 50, I add 60, I add 100. At 100, every enzyme is going to be working. If I go up now and I add 10,000 substrate molecules, I still only have 100 enzymes ripping. So at this point, it plateaus. The rate, the speed at which my reaction can go is maxed out. What do we call that? Saturated. So at this point, every enzyme is working at its maximum speed. The enzymes are saturated. And if I added 10,000, 5 million, whatever, substrate molecules, it wouldn't matter. It's sort of like you go to the grocery store and you go to Walmart and there's all these cashiers and you can go wherever you want. And then you add more people and you add more people. Eventually you get to a point where every cashier is ringing people up. You're going to have to just wait in line. And that's basically what's happening here. The other two lines are showing the difference between a competitive inhibitor's effect and a non-competitive inhibitor's effect. So a competitive inhibitor, in fact, we're going to skip to this next picture. So this is a competitive inhibitor. A competitive inhibitor slows the enzyme down because it looks enough like the substrate that it sort of competes with it for the active site. Typically, this is not necessarily a permanent thing, but this is obviously going to slow the enzyme down. If you have a bag full of blue molecules and red molecules, the more blue ones you have, the slower the enzyme is going to be. The more red ones you have, the less effect the blue one is going to have on it. Does that make sense? Adding more red ones, then the chance of this blue one getting in the way is going to be much, much lower. The enzyme probably won't even find a blue one because there's so many red ones around. So this graph, going back, competitive inhibitors, if I add a little inhibitor, the more substrate I add, I'll get to a point where the inhibitor has almost no effect at all because there's so much substrate around that those few inhibitors are probably not going to get in the way. Non-competitive inhibitors work different. Non-competitive bind to another site on the enzyme. Sometimes it's called an alternate site, or you might want to know the term, sometimes it's called an allosteric site. The bottom line is they change the shape of the active site on this enzyme. So if I had 100 enzymes in my little diagram previously, if I add 50 non-competitive inhibitors, basically 50 of my enzymes are going to get shut down. Their active site doesn't work anymore. It's not going to matter if I add more substrate because I now have less enzymes working because everyone that bound to a non-competitive inhibitor, its active site is closed. So this is the effect of a non-competitive inhibitor. Enzymes that bind with the inhibitor are no longer functioning, so the maximum rate goes down depending how much inhibitor I add. Obviously, there's no numbers here. You could say, well, why is it there and not up here or down here? It would depend how much inhibitor there was. But the bottom line is what they want you to see from this graph. Know that if you see these lines, that for a competitive inhibitor, adding more substrate will overcome it. For non-competitive, it's going to plateau somewhere lower than the regular one, and adding more substrate is not going to speed things back up. That's what you have to understand from this picture. Good question. If you added more enzyme, then yes, the whole rate would go up. Adding more enzyme would have, basically you've increased the number of factory workers. So adding more enzyme would make all of these lines go up higher because the maximum rate would be higher. If I say, oh wow, it's getting really crowded at Walmart, we're going to open 5 more cashiers, I basically raised the whole thing. So there you go. If I adding more substrate for competitive inhibition will overcome the inhibition to the point where it could actually reach the regular rate. Non-competitive, it can. All right, we already went over this slide, so just understand the difference between how the two inhibitors work, competitive versus non-competitive. And that brings us to this one. So this is the one everybody screws up because they look at this here and they say it's saturated. This is not saturated. This is different. So this is how much product is being made over a period of time. So this is sort of like you guys ripping papers. First, during which time period are you ripping papers the fastest? Where's the most product being made? Time 2, right? In this time period, you can see a lot of product. The amount of product is increasing a lot. If you were to calculate with numbers, you could calculate the rate. The rate would be the highest here. This is not saturated. This is where the reaction is finished or it's reached equilibrium. Pretty much the enzymes are doing nothing here. In other words, this is sort of like you guys ripping the papers. Once you ripped all 50, the amount of product made would have stayed 50. And if I had left you there for 10 minutes and said time how many you rip over 10 minutes, for that last 6 minutes, this would have just stayed here at 50 because there weren't any more to rip. Yes? No, because saturated means the enzymes are working as fast as they can. So for that extra 6 minutes, the rate would have been 0. The enzymes, you would have been doing nothing. Remember, saturated means you're ripping as fast as you can. Technically, in this graph, saturated is here. This is when you were ripping as fast as you could. Also, notice here, it starts to slow down. That's because if you've already ripped 48 of your 50 papers, now to find those last 2, you had to find them among 94, 96 ripped pieces of paper. So a rate is going to slow down as you start to run out of substrate. The rate's going to get slower. Olivia, did you have another question? Okay. So please be careful. Pay attention to the labels. If it's how much product is being made, this plateau is not saturated. This plateau is where the enzymes are finished. They're not doing anything here. Saturated is when the most product is being made. So technically in this graph, and I wouldn't ask you where is it saturated, but I could ask you where are they working fastest. It's here in section 2. You're seeing the most ripping going, or, I say ripping because of our lab. This is super easy. This should be a giveaway on the test. If you're asked what the optimum temperature or pH for an enzyme is, really easy. All you have to do is find the peak of the graph. So if we look, I'll just go over this one really quick because I know we're a little short on time. I estimated for enzyme 1, I don't know, maybe 3.8-ish. I don't know what you guys came up with. Does that sound good? Give or take. I would accept any logical answer. How about enzyme 2? Around 6, and enzyme 3? Around 9. It's just the peak. Now, if I say, does enzyme 1, the red one, does it work at pH 5? Yes, it does. Not as well, but it does work. Does it work at pH 7? No, because that's outside of its range. So it works anywhere under this little hump here. This enzyme works all here. But its peak, its best optimum would be 3.8. Is there a pH where all 3 enzymes work? No. So some people were getting this wrong. If I color this in, you'll see there's no spot where all 3 here, there's no place where all 3 colors overlap. Therefore, there is none. However, what is the range for enzymes 1 and 2 both working? Yeah, give or take, you should have come up with somewhere around the range of, 3.8 to maybe 5.6, something like that. In other words, anywhere here where the 2 overlap, both of those enzymes were working. Be careful, because I had somebody say, oh, well, wouldn't it just be anywhere from 4 to 9? And the answer is no, because this enzyme stops working here. So you can't go past this point for this enzyme, and then this one stops working here. So it has to be where the 2, when I color code it, you can see it more clearly, I think, where the 2 overlap. Does that make sense? This should be super easy. Honestly, this is like meant to be easy. All right, rate. To calculate rate, this is the formula that's not provided for you. Amount 2 minus amount 1 over time 2 minus time 1. Don't forget units. Units on this are just going to be whatever units are your amounts and your time. So for this one, milliliters per second would be the proper units. I don't have 0 up there, but you should know how much would have been ripped at time 0. 0, because you didn't start yet. So technically 0, 0 is a given, even if it's not on the chart. So 0 to 10 seconds would simply be 2.5 minus 0 over 10 minus 0, which is 2.25. milliliters per second. From 30 to 40 seconds, you just look at your 2, so it's going to be 6.5 minus 6.0 over 40 minus 30, and that's going to give you 0.05 milliliters per second. So does that make sense? It's just calculation. Just make sure you know the formula, and make sure, you include your units. And again, just like our lab, if you were to graph this, you would see that this is slowing down. And if I let it keep going, it would probably plateau, because this would be the progress of a reaction. Eventually, the substrate's all broken down, the reaction's over. And it's going to get slower near the end, because it's going to be harder to bump into substrates because you've got all this product building up. And that brings us to the last one. So this formula is on the formula sheet. So you will have this one available to you. Biggest mistake, don't forget if it's negative, to put a negative sign. Don't forget units. And don't forget to change your temperature to Kelvin. So this one's just going to be 2,500 minus 293 times 10. Sorry, it's negative 430. Would it be spontaneous? Yes. All right, that's it.